Hello, this is part 2 of chapter 9. I'm still dealing with bonding. In this particular topic, we'll be talking about molecular orbitals and hybridization. So, valence bond theory explains the bonding between two atoms from overlap of half orbitals. We've talked about, in the past, we talked about Lewis structures, which can explain bonding as well. We talked about valence shell electron pair repulsion, which explains the shapes based on the electron repulsion. And now we introduce hybrid orbitals. So if we look at two relatively simple compounds, HCl and H2, they have different bond lengths and different bond strengths. And the previous two theories of Lewis structures and valence shell electron pair repulsion, Vesper, it cannot explain this. So if we look at the HCl, we have the 1s overlap with the 3p. So if we remember from our chapter 6 electron configurations, we have here 1s from the hydrogen, and then with the Cl we have 1s2, 2s2, 2p6, 3s2, 3p5. We only focus on the outer shell, so the level 3. And we have here for HCl, we have one of the 3p orbitals. It has one electron available, and it will overlap with the 1s electron from the hydrogen. So again, the 3p orbital will overlap with the 1s electron, and we have this bond here that's formed. In this likely same case, we have for H2, we have a 1s1 and a 1s1 combining, a 1s1 and a 1s1 combining, and we have this H2 molecule when they come together. So here we look at simple case of H2, which is composed of two hydrogen atoms. Here we have the graph of energy versus the distance between the H atoms. So if we label this the first hydrogen and this one the second hydrogen, if they're very far apart from each other, there's no attraction. However, as they become closer and closer together, the attractive forces increases, and that's because the electron in the first hydrogen gets attracted to the nucleus of the second hydrogen. The nucleus is made up of a proton, so negative and positive attract each other, and conversely we have the electron in the second hydrogen attracted to the nucleus of the first hydrogen. So this continues until about 74 picometers distance. And if we continue this, if we bring it even closer and closer, what's going to happen is there's going to be a lot of repulsion starting to form, because if the atoms are too close to each other, you have repulsion between the electrons and you have repulsion between the nuclei, the two protons between H1 and H2. So there's a balance, and they've determined that the ideal bond length calculations is 74 picometers, which has an energy of negative 436 kilojoules per mole potential energy. And this is also where H2 molecule is most stable at 74 picometers. So hybridization, just like a hybrid car, it means it runs on both gas and electricity. If we convert this idea of hybridization, hybrids in our case, we'll look at the S and P and Ds, but in this case of sp3, what happens is an s orbital combines with 3 p orbitals. I'll repeat. In this case, for sp3, one s orbital combines with 3 p orbitals. Let's look at the structure CH4. This is the Lewis structure, if you recall. Has 8 valence electrons in total. We know from VSEPR the angles are 109.5. And if we focus on the carbon in this molecule, the central atom, we have a 1s2, 2s2, and 2p2. The VSEPR shows, and the Lewis structure shows, that there are 4 bonds. But here, we only have 2 available orbitals, which have 1 electron to make the bond. But as I said, we have 4 bonds. So the electron here will jump over here. And now we'll have 1, 2, 3, 4 available orbitals to make the 4 bonds with the hydrogen, the 1s electrons. So as I just said in a more detailed diagram with the colors, we have here the blue combining with the red. As I said, this is an sp3, so an s orbital combines with 3 p orbitals to give us 4 purple sp3 hybrid orbitals. So again, hybrid, the s and p's come together. The blue and red come together to give us 4 sp3 purple orbitals. They all have the same energy, and each one of these hybrid orbitals can now take in a hydrogen, an electron from the 1s to make 4 bonds. Also, you notice here the angle is 109.5. If we had left these unhybridized, meaning they didn't combine, the s and the p's, we know that the angles between the px, the py, and the pz, the angle between those 3 orbitals is 90 degrees. And we don't experience that. We see experimentally that it's 109.5. So one way to explain that is through these degenerate equal energy hybrid orbitals forming. Again, a nicer picture. The 3 p orbitals hybridize with the s orbital to give us these purple sp3s. So there are 4 sp3s. Let's look at another example, NH3. We know the Lewis structure here has 3 bonds, 1 lone pair. It has a total again of 8 valence electrons. And the way we explain this through hybridization is still 3 p orbitals come together with an s orbital to make 4 sp3 hybrid orbitals. These 3 are involved with overlap with the hydrogens, and you're left with the lone pair that does not react with anything that is on its own. So the second case is sp2, and as the name suggests, we have 1 s orbital combining with 2 p orbitals to give us sp2 hybrids. Notice the complexity of this slide. We have a blue orbital combining with yellow to give us green. And what's left over is a p orbital that's unhybridized. The greens have equal in energy. An example we'll look at is boron trihydride. So in this case, we can also look at boron trifluoride. The case here, we have, if we look at the boron, if you remember, it's 2s2, 2p1. However, we have 3 bonds. So how do we explain those bonds? One of the electrons jumps into an empty p, and these 3p hybrids form. And now the electrons from the, in this case, fluoride, or you can say hydrogen as well. I guess we'll look at the hydrogen. Now the 3 electrons from the 3 hydrogens can come in to form bonds, and we're left with an empty p orbital. So this is a 3-dimension. This is the bird's eye view, looking from the top. This is one of the p, this is pz. It can be arbitrary, it can be px or py. In this case, they chose pz to be unchanged. Third one is sp, meaning we only have one s orbital combining with one p. And if we look at beryllium trifluoride, beryllium difluoride, we always focus on the central atom, which is beryllium. It's 1s2, 2s2. So we focus on the outside, the valence electrons. What's going to happen is one of these electrons will jump over here. These 2 orbitals combine and form a purple hybrids. They both have equal energy, and you have 2 unhybridized p orbitals. So what happens here is there's an overlap between the s orbital combining with the p's to give us these sp hybrids. Again, we call it sp because it's only one s combining with a p to give us our bonds here. So looking at below, the electron from the 2p of the fluorine combines with an sp hybrid of the beryllium. We have another example. This is a bit more complex. It's called sp3d hybridization. So as the name suggests, we have an s combining with 3 p's and a d. So the case is phosphorus pentachloride. This is the Lewis structure here. We focus on the central atom, and if we look at the phosphorus, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. However, we know in PCl5 there are 5 bonds. So how do we explain for those 5 bonds? Well, we have to include the 3d orbitals, which are empty at this moment. So what happens is the electron, you can think of this as the s jumping over here. They all combine. The blue, the 3 red ones, and 1 white one combined to give us this light purple. So I'll just use the color as a analogy when you mix these 3 colors. But what happens is it hybridizes. One of the s's hybridize with 3 of the p's and 1 of the 3d orbitals to give us 5 sp3d hybrid orbitals, all with equal energy. And again, you're still left with 4 3d unhybridized orbitals that remain. So now these sp3ds can combine with a chloride. Each chloride comes in to make a bond. You remember in a bond, there's 2 electrons. So these bonds are formed from the hybrids on the central atom with the 3p orbital from the chlorides. This is a nice diagram. What happens when they combine? And we recall there's a trigonal bipyramid electron domain for the PCl5. And we'll go through this a second. If you recall, for the sp, it's a linear shape. For the sp3, it's a tetrahedral electron domain. And for the sp2, it's a trigonal planar electron domain. And the last one I'll mention here is sp3d2. Hopefully you can follow and realize there's an s orbital combines with 3p orbitals, combines with empty d2 orbitals, or two of them combine, and we have here a hybridization to give us 6 sp3d2 hybrids. And this could work for the SF6, if you recall from Lewis structures, SF6 sulfur hexafluoride. If we focus on the sulfur, it's 1s2, 2s2, 2p6, 3s2, 3p4. This electron would jump over here. You can think of it as the electron from the 3s also jumping over here, and then the orbitals combine to give us this sp3d2, all with equal energies. This is another diagram. The d orbitals that are used to form sp3d2 are the dz squared and the dx squared minus y squared, the orbitals along the axes. So that's a little bit about the theory behind how they form, but you'll be given examples on how to identify the hybridization. So we use the electron domains to figure out the hybridization on the central atom. So for instance, we look at linear, it corresponds to an sp. The trigonal planar, as I said, an sp2. If the electron domain is tetrahedral, we have sp3. Trigonal bipyramid, sp3d, and octahedral, 6 bonds, no lone pairs, sp3d2. So for instance, if you had something like water, we know the shape of it is bent. But if we're looking at electron domains, it has 1, 2, 3, 4 electron domains. This would be a tetrahedral. I'll repeat, this would be a tetrahedral in terms of electron domains, and it would correspond to sp3 hybridization for the oxygen. So let's go back. We already drew the Lewis structures. We already have the shapes for these, so I can go through this rather quickly and determine the hybridization on the central atom. So for water, I just talked about, it would be an sp3 because it has a tetrahedral configuration. Again, just to remind you, these will be posted on Blackboard, so which will give you a step-by-step how I came up with the answer. The CCl, this is not in too much detail that you need to figure this out because you've already drawn the Lewis structures. For the CCl4, we know this is a tetrahedral, no lone pairs, or actually you don't have to worry about the lone pairs, you count them as a group, electron domain group. So for the CCl4, this would be sp3 as well because it's tetrahedral. The NF3 would be tetrahedral. Let me write this out here, tetrahedral. Tetrahedral electron domain. We know the shape is a trigonal pyramid. However, the electron domain is tetrahedral. There's 4 groups attached to the N. So this would be an sp3 as well. sp3 for the following. The CH3F would be sp3. In this case here, this is a bit different. We have the C2H2. It's drawn out like this. It's triple bond, H2. Again, we look at the central atoms. This is linear. Each carbon is linear. Therefore, it is an sp hybridization for SCN, and NH4 for the SCN. If we focus on the central atom, it's going to be sp as well because they're linear. The carbon is linear. And for the NH4, It has 4 bonds, 4 groups attached, tetrahedral and electron domains in terms of electron domain. So this would be an sp3. We're going to talk a little bit in more detail about the C2H6 in the SCN- in terms of its hybridization, double bonds and triple bonds, but that'll come up in a few slides. Well, we'll just go to the next slide about double bonds and triple bonds. So in this case, we have the example of C2H4, which has 1 double bond. If we focus on, let's call this carbon 1. If we focus on the carbon 1, normally it's 1s2, 2s2, 2p2. And what happens here is an sp2 is formed where one of the s's combines with 2 p orbitals to make 3 sp2 hybrids. And what's left over is an unhybridized p orbital. And this unhybridized p orbital will be involved in the double bond characteristic with the carbon 2 unhybridized p orbital. So what happens here is, again, I'll just repeat. We can look at carbon 2 now. Carbon 2 has the same electron configuration, 1s2, 2s2, 2p2. And to explain that, the s orbital hybridizes with 2 p orbitals, and you made 3 sp2 hybrid orbitals. And 1 is left over. Again, this will form double bond with the unhybridized p orbital from the first carbon. So to take it a step further, we have introduced something called a sigma bond. Okay, so let's write this out. The sp2 for carbon 1, carbon 2 is also sp2. There are 3 bonds that form on the sp2, and then there's 1 that's left unhybridized with an electron inside. Again, that's going to form our double bond. But if we just focus on the sp2 hybridized ones, we have something called a sigma bond, which is a covalent bond formed by direct overlapping of 2 adjacent atoms on the axes, the internuclear axes. So in this case, for this, if we call this a C1, the first carbon, and we call this the second carbon, there's overlap between the sp2 and the sp2, and we can equate that to this bond right here. There's also an sp2 orbital overlapping with a 1s from the hydrogen, an sp2 from the carbon overlapping with a 1s orbital from the hydrogen, and that also occurs on the carbon 2. So this is a sigma bond. These are the single bond here is a sigma bond, and then the third sigma bond here. And we're left with 1 bond above the axes, which is not a single bond. And we'll talk about this in the next slide. We call this a pi bond. So this is not on the axes here. It's above and below. And it's an interaction of the unhybridized electron, unhybridized orbital from carbon 1 overlapping. So again, this is still carbon 2. This is carbon 1. There's overlap above and below with the electron here. And this is what forms a double bond. So the sigma bond is the more stable between the two, direct interaction on the internuclear axes, and you also have some pi bond, which comes out for the double bond. So overall, if you compare a single bond with a double bond is stronger, but individually, the sigma bond is stronger than the pi bond. The pi bond is overlap above and below the axes versus direct sigma bond. A lot of yellow there in the slide, but versus direct overlap. This is maybe a nicer diagram. Here we have, again, the pi bonds interaction above and below, made up of one electron from the carbon 1 and one electron from the carbon 2. You can either be above and below or in and out of the plane. Either one is fine in terms of the overlap. And then we have these sigma bonds here, which are direct. Sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. So the question to you was how many sigma bonds are in this C2H4 molecule? You would say there are one. I can do it here. If I draw this out, double bond. If the question was how many sigma bonds are in this molecule, there would be 4, 1, 2, 3, 4, 5 sigma bonds, so 5 sigma bonds, and there would be 1 pi bond here above and below, 1 pi bond. We take it a step further and now look at a triple bond. It's an sp. What happens is, again, we look at the carbons, carbon 1 and carbon 2. The carbon electron configuration is 1s2, 2s2, 2p2. So an S and P come together to make two sp hybrids. What's left over is you'll have 2 electrons which are unhybridized. These will form the pi bonds. You have 2 sigma bonds for one of the carbons, and for the other carbon you have the same situation where you have 2 sigma bonds, 2 sp hybrids, and 2 unhybridized orbitals. So the ones in purple will make a single bond. Let's see if I have purple. I do. This will make a single bond, and it will make another one with the hydrogen. And these white ones here, so I have white, they will form above and below to make the double bonds. This is the pi bond interaction. But we have another pi bond interaction. This would be along in and out of the paper. So there's pi bond interaction there as well to make the triple bond. So again, hopefully a nicer diagram. We have here the C2H2 Lewis structure, which is composed of 1 sigma bond, 2 sigma bonds, 3 sigma bonds, so 3 sigma bonds, and 2 pi bonds along the XY, where you can say above and below the plane and in and out of the plane, and 2 pi bonds. Overall, the single bond is weaker than the double bond, and it's also, the double bond is weaker than the triple bond. In terms of bond lengths, it's the opposite. The triple bond is the shortest compared to the double bond, compared to the single bond. So in terms of bond length, the single bond is the longest if you're just comparing the same elements. So let's try the CH2O. You can pause if you want to try on your own. We're going to focus on the carbon and the oxygens. Let's draw this. This is the Lewis structure. If If we look at the carbon in the middle, it has electron domain of trigonal planar, 3 electron domain groups. So this corresponds to an sp2. Lone pairs here. This would be an sp2 hybridization on the carbon. How many sigma bonds? We have 1 sigma bond, 2 sigma bonds, 3 sigma bonds. And how many pi bonds? We have 1 pi bond here. If we look at the next example, we have acetic acid, CH3. I'll draw the Lewis structure. OH2. So we call this the first carbon, the second carbon, call this the first oxygen, the second oxygen. If you look at the first carbon, it has a tetrahedral electron domain, 4 groups attached, so this would be a sp3. We look at the second carbon, it has 1 group, 2 groups attached, 3 groups attached. This would be an sp2 in terms of electron domains. This oxygen up here, because of the double bond, will also be sp2. And this third one here is a tetrahedral, 1, 2, 3, 4 groups attached. This would correspond to an sp3. If the question was how many sigma bonds, how many pi bonds, I'd count, let's do this in yellow, 1, 2, 3, 4, 5, 6, 7 sigma bonds, and 1 pi bond. If we look at multiple bonds, continuing on, this is for those of you planning to take organic chemistry, benzene, which is C6H6. This is a nice diagram here on the right. We have here resonance structures as well. We have 6 carbons and 6 hydrogens. And in terms of the carbons, we have a single bond, and then a double bond, and then a single bond, and then a double bond, single bond, and double bond. And these form a resonance structure here. So the double bonds have moved over 1. And one way to write these 2 out in resonance is this structure here. Again, there's 6 carbons. We don't draw the hydrogens in this format, the skeletal format. We just show the carbons, and this circle here represents the resonance where the double bonds shift from one carbon to another. So we have 6 unhybridized 2p-z orbitals. The double bonds are above and below the plane, and I'll show you the next slide. But each one of these carbons is trigonal planar, which is sp2 hybridized. So each one of these carbons is sp2 hybridized. So if we have here again still benzene, C6H6. We have the double bond, we have the single bond, double bond, single bond, double bond. This is the side view, and double bonds live above and below the plane. So this makes, as we talked about earlier, the double bond is stronger than the single carbon-carbon bond. So this makes the benzene relatively stable. And looking from the bird's eye view, here the top view, we see electron densities around the carbon. This is due to most of the double bond around the carbons. However, there's overlap above and below the plane as well to help the stability of the benzene ring. This is what you see from the side point of view. The double bonds above and below. This is, the title says the delocalized pi orbitals. These are the sigma bonds which are on the nuclear axes. So the last set of orbitals, not hybrid orbitals anymore, we have molecular orbitals. So in terms of molecular orbitals, they have a maximum of 2 electrons per orbital. The electrons in the same orbital have opposite spin. We're now talking about the arrows. They have opposite spin, just like when we're talking about orbital diagrams, and they are defined by the energy. So one new point with MO, we can say molecular orbitals, is whenever 2 atomic orbitals come together, one bonding orbital forms and one anti-bonding orbital forms. Bonding orbitals helps with the bonding, and as the name suggests, anti-bonding is the counter of the bonding orbital. We say destructive interference. With the bonding molecular orbital, if we think of the electron as a wave again, so if we have the electrons traveling in waves, if we were to combine these two, wave 1 and wave 2, they're in phase. We call this constructive interference, where they add up and they help with the overlap. And we would call this constructive interference, and there you can form a bond. We'll talk about the most simple example between 2 hydrogen atoms coming together. So constructive interference, when 2 electrons are in phase, they add up and they form a sigma bond. We have the opposite. We have something called an antibond, which is destructive interference. Here the waves are out of phase, so when we add these 2 up, they will cancel each other out. So we have a bonding orbital and we have an anti-bonding orbital. So when anti-bonding orbitals are formed, there's no connection between the atoms, therefore it doesn't promote bonding. And we just designate this with sigma star. And when they don't bond with each other in anti-bonding, we call this a node, where there is absolutely 0 electron density between the 2 atoms. So what did I say at the beginning? We have 2 orbitals, atomic orbitals coming together to form, here's the atomic orbital, and another atomic orbital. Let's look at the most simple case of H2, which is, as you guys know, 1 electron and 1 proton for each hydrogen. When they come together, they form 2 molecular orbitals. One is a bonding orbital and one is an anti-bonding orbital. The bonding orbital is more stable, therefore it is lower in energy, versus the anti-bonding orbital, which is higher in energy. So when the electron from hydrogen 1, let's call this hydrogen 1, combines with hydrogen 2, when they come together, they will sit in the more stable orbital, which is the bonding orbital. So they will form a bond, and as you guys know, H2 does exist. This is the most stable, where the 2 electrons fit the lowest in energy. When we talk about later other molecules where you have more than 2 electrons, some of them will enter the some will enter the sigma star up here. We'll talk about that later in a second. So another diagram here again for H2, the molecular orbital energy diagram. When 2 atomic orbitals come together, they form 2 MOs. One is a sigma and one is a sigma star. Constructive interference in this case, and destructive interference, anti-bonding molecular orbitals. We can numerically we can quantify its stability using bond order, and the formula we use is 0.5, 1 over 2, 0.5 times the number of bonding electrons minus the number of antibonding electrons. So, and again, the most simple case of H2, it has 2 electrons, as you know, 1 from each hydrogen. They will fit in the bonding electrons down here. So the equation will be 2 minus 0, because there are no electrons in the antibonding. 2 minus 0 divided by 2 is 1. So the bond order for this is 1 for H2. If you were to, the question here is, what would you do if you added some UV light to the H2 molecule? Well, in theory, if you added some H2 light, one of the electrons, I'll do this in blue, one of the electrons would get excited. It would go up to the antibonding, and then you would have now 1 in the bond, 1 in the stable sigma, and then 1 in the unstable antibonding MO. 1 minus 1 will give you 0, so the bond order would be 0. Very unstable molecule, H2, an excited H2 molecule. And then it'll start reacting, which is unstable. So let's look at He2. This is a total of 4 valence electrons. So here's a nice diagram. 2 here from the first helium, 2 from the second helium. When they combine and make molecular orbitals, 2 of them first go into the more stable constructive interference, MO, and then the antibonding MO to make a total of 4. If we do the math, it's going to be a half. 2 from the bonding minus 2 from the antibonding gives us 0. So the bond order is 0, and He2 is not very stable in general. Okay, if you remember, it's a noble gas. He, it's very happy with just sitting on its own because it has 2 electrons in the 1s orbital. So He2 doesn't exist. The bond order shows that because it's a bond order of 0, and He2 does not form. The question for you, so let's place in order the increasing stability of the following compounds. H2 plus, when you have a plus, that means you lose an electron, so you only have 1 electron there. H2, He2 plus, that would be 3 electrons, and He2, which we just did above here, would be 4 electrons, and we would use the bonding and anti-bonding MOs to figure out the bond order. So I've drawn this out for you for each case. This slide. We have H2 plus, we have H2, we have He2 plus and He2, so you guys can figure out the total number of valence electrons. We place them first in the most stable one, so the bond order for this first one, H2 plus, there's only 1 electron here. The bond order would be 1 minus 0 times 0.5 or divided by 2. So the bond order here would be 0.5. The bond order for H2 would be 1 because it's 2 minus 0 divided by 2 or times 0.5 would equal to 1. So the bond order for He2 plus would be 2 minus 1 divided by 2 would equal to be 0.5. And the last one here, He2, it would be 2 minus 2, which is 0, divided by 2, which is still 0. So if we look at the bond order, we compare 0.5, 1, 0.5, and 0. So the most stable one would be H2. The least stable one would be the He2. And comparing the 0.5 between the H2 plus and the He2 plus, the He2 plus would be less stable because we have 3 electrons here, and it's slightly less stable intuitively because we have electrons which are closer together, more repulsion, and therefore would be less stable. And that concludes our chapter 9.